James Hunter, who's joining us from Los Alamos National Lab and across several time zones, is the team leader for the special projects team within the non-destructive testing group at Los Alamos in northern New Mexico in the States. The NDT group runs about 15 CT systems at any given time and uses or oversees a number of others as well. James has 20 years of experience in CT and currently serves as the subject matter expert in this capability for Los Alamos. He started his career there writing a large portion of their CT reconstruction code, including implementation of dual energy solution and reconstruction. He then transitioned into technique and system development and has worked in a range of CT areas from micron and sub-micron resolution synchrotron imaging all the way up to developing Los Alamos's 6 to 20 MeV high energy CT system, which I know a number of people here are interested in, and a fast neutron imaging systems at the LANSCE accelerator facility. And today, James leads the special projects team, which develops imaging and tomography systems to fulfill new requirements in support of Los Alamos and the broader US development of energy complex. His most recent focus includes improving the high energy 2D detectors for their use with that 6 to 20 MeV range to support an increasing demand in this area. So over to you, James.
Definitely. Great, thank you. And I'll apologize if I'm rough at all, because definitely giving a presentation this way is kind of new to me. So we'll see how it goes. Let me know if anyone has issues with the video or the audio. So yeah, I'm going to give an overview of sort of our imaging capability, because I think it's a little bit unknown. And then I'm going to talk about MEV X-ray computed tomography in practice. And so we've been doing high energy CT for about 8 years now. And we've been running MEV radiography for, oh gosh, probably 50 or 60 years. So we've been in this area for a while, but the CT is fairly new. So with that, I'll give an introduction background, do some high energy basics, just because your intuition on X-ray imaging starts to fall apart a little bit at higher energies, and then particularly for high energy neutrons. Really only going to touch on the neutron area because we've done a little bit at that, but it just hasn't worked as well as we'd like. And then I'll go over, 5 different example data sets. And I'm really focusing on the data we got and sort of the quality, what we've achieved, not so much on the modeling side. We've done some transition all the way to a full model from high energy CT data, but it's not real common, and I just didn't have any great examples. And then just a little bit on sort of, where we want to be going, because the high energy quality is not quite as good as we'd like for CT. So with that, a little bit of introduction. I think you guys can see my mouse, right? So I can use that as a pointer. So if you're not familiar, perfect. If you're not familiar with it, Los Alamos National Lab is in the United States. We're in the state of New Mexico. So right here, about, a couple hundred miles north of the border with Mexico. This is a picture of just sort of the central part of our campus. We're what's called a federally funded research and development center. So that means we're almost entirely US government funded. We've got, the numbers keep changing. We're actually growing quite rapidly right now, but somewhere in the vicinity of 13,000 employees. And then this summer is a little weird, but normally we have about 1,600 students on campus each summer. The actual lab is 40 square miles and about 1,000 buildings and running about $3 billion budget. So, people frequently say, oh, I know so-and-so at Los Alamos, and it's a huge place. So unless I overlap in work area, it's kind of hard to really connect. But going down from there, we maintain a full-time non-destructive testing group. We actually go all the way back to the Manhattan Project as a group. So the capability of needing X-ray and NDT has been recognized here for the entire life of the laboratory. And, technique-wise, that's radiography, CT, ultrasound, eddy current, dye-penetrant, nuclear magnetic resonance, X-ray fluorescence. So we really dabble in a lot of stuff. I'm focused almost exclusively on computed tomography, a little bit of digital radiography. We have a CT production team, and then so they're responsible for scanning parts, giving a customer, whether it's the part's good or bad, whether they need a dimension, whatever it is. I believe they broke 10,000 parts scanned last year. So we have a fairly large operation. And then we have what's called the special operations team. And it's, what is this adding up to? Really about 6 people. And our job is when a requirement comes in that we can't currently meet, we work on that to develop a new technique, a new imaging system, whatever it takes to meet that requirement. And I'm team leader for that team. So loosely speaking, we're about a 20-person CT effort, and it's becoming where CT just dominates the NDT area at Los Alamos. Once people get a 3D, they really want to, they really don't want to go back to a 2D image. So just, I don't really want to read this entire thing, but just to give you an overview, we kind of have a range of systems. So obviously a lot of microfocus cabinets. We're an old enough facility. They started out building large shielded concrete bays for holding a lot of our sources. So we have 3 or 4 different bays that have 450 kilovolt sources, and then we put some microfocus in there as well. A really unique machine, which there's a photo of it right here in the center, is this thing called a Microtron. So this was originally made by Scintillator in the early 1980s as a cancer therapy treatment machine. And we've had it modified to be an industrial imaging source. It's adjustable right now between 6 and 20 MeV. You could actually go as high as 22. You can change the step size to half MeV increments, but these are the presets we have in place. We also run a couple other LINACs. We're in the middle of commissioning a new Varex 915 LINAC. So that's kind of our high energy sources we're going to focus on. And then we do a broad range of imaging at different facilities across the country and a little bit in Europe as well. And then, you know, we're primarily using an in-house reconstruction code called Recon, or we use the North Star Inc. builds a lot of our cabinets, so we just use their packaged reconstruction software. And then Volume Graphics tends to be our default visualization. We've also used this package called Dragonfly. And I think the only other thing I want to really highlight here, so I do show a little bit of data from LANSCE, the Los Alamos Neutron Science Center. So this photo right here is that. The accelerator starts right where my mouse is there, and it runs all the way down here. And then, so that's an 800 MeV proton beam, and it turns, it goes under the road, and there's a target. Let me see here. It's actually right about in there is the target that generates the fast neutrons I've used for imaging. And so the point here is, you know, there's like, so the ISIS source in the UK is it was actually made by a guy that worked on LANSCE and then went back and built a copy with some modifications. Other than that, I mean, there's like 3 fast neutron sources in the world at this kind of flux level. And so the point I'm making is you don't hear about fast neutron imaging because there's basically no sources, and running this thing is an enormous budget, and it's just incredibly expensive to build. So, you know, they do exist, but there's very few in the world. So that's sort of the quick overview of hardware. You know, I sort of put this together to put everything in perspective. I'm going to talk about the Microtron and MeV LINACs, so sort of figure 6 MeV plus. I'm also going to talk a little bit about fast neutron. I always already highlighted that's rare. Both of these are really pretty uncommon. There's a few facilities in Europe that have, I think, typically 4 and 6 MeV LINACs for imaging. There's, I guess, 3 commercial facilities in the United States now that have these, but they're quite uncommon. And so most of what you see presented on is sort of in this synchrotron sources, microfocus, 450 kV tubes, and then nuclear reactors tend to do a fair bit of imaging with low energy neutrons. So that's sort of the spectrum of sources we deal with. Okay, so I want to just step back and go a little bit into sort of the basics of how high energy imaging works and where that starts to lead to some headaches when it comes to getting it to work well. So I really struggled with explaining this to people why it's hard. And so I finally stepped back to this concept called a half value layer, which is hopefully familiar, or at least loosely to a few people. This is used in imaging quite a bit. It's, I think, used maybe a little more in the medical radiography community. But the concept of the half value layer is just that's the thickness of material for a given energy of X-rays, at which on the other side, you only have half the X-rays left. So if I have an energy, I put up like, say, a centimeter of steel. If I started with 1,000 X-rays, I end up with 500. That centimeter would be a half value layer. So it's also turns out to be real convenient because people these days are good at thinking in powers of 2. And so 2 to the 16 would be cutting your number in half 16 times. So it fits well with the computer storage scheme. The second thing that's really important with high energy and is, I think, pretty rarely appreciated is that the interaction cross-section actually goes up after a certain energy with X-rays. And so there is a most penetrating X-ray, and after that, you start getting less and less penetration. So what I did is I took the attenuation tables off the NIST database on these figures on the right and just plotted them up. And what I'm showing here, so this one was copper, which is, people think of copper as being a little bit of a pain to image typically. So this point right here, which is, I wrote it down somewhere, 8 MeV, so just below 10, is the highest or the lowest interactions, the highest penetration energy for copper. And as you start to go up, it turns out pair production gets more likely. And so anything above 8 MeV is less penetrating than 8 for copper. If you look at lead, you get the same thing, but it's down here around, so it's about 4 MeV right there. So what this means is just tuning the energy up doesn't always help you. At some point, you hit the limit. So when we say we have 20 MeV, we get a broad spectrum. And what we're actually doing is we're increasing the number in this area. We don't care so much that there's a 20. We care that we get a lot more right here. But fundamentally, what this means is there's a thickest part you can image, and after that, you're done with X-rays. There is a final point because it's limited. It doesn't just keep penetrating more and more. So what I do here, and I don't want to go through all the math, but I work through the half value layer calculation from attenuation to show, kind of what a thickness means in terms of number of X-rays. So for copper, the half value layer works out to about 2.5 centimeters. So if I started with 1,000 X-rays, go through 2.5 centimeters of copper, this is the ideal energy. So at the 8 MeV, after 2.5 centimeters, you now have 500 X-rays left. For lead, it's 1.4 centimeters, so getting noticeably worse, right? Lead's denser, higher atomic number. So now I think, well, what if I had 10 half-value layers? So that means if I had 2 to the 16 X-rays, I'm going to be left with just 2 to the 6 now. And that, if I just multiply by 10, that means 25 centimeters of copper, or because I'm in America, I think of it as about 2 feet, or not 2 feet, what does that work out to? 10 inches. Is going to give me 10 half value layers, or about 14 centimeters of lead, or so. What is that? A little under half a foot. So detectors are 16-bit, right? That's typically what you get today, and they're not usually really 16-bit, but that's a good approximation. So if your detector were somehow ideal, which it isn't, you started out with 2 to the 16 photons, you had only the ideal energy of X-rays. After you get through these 10 half value layers, you now have 64 photons left. And what that is really bad statistics. So you add in the fact that you don't have an ideal spectrum, and now you also have scatter. And scatters, I'll have a slide on that. This means that somewhere in the vicinity of 10 half value layers is really getting to be maybe not impossible to image, but very, very hard. And so keep that in the back of your head for high energy. There is a limit, and this sort of math is what drives that. You're going to hit a point where you just aren't getting any X-rays through, and then scatter, background noise, and so on kill any signal you had left. So the good rule of thumb is that if you have about 100 grams per cc of material, that's not too hard to image at high energy. 200 is pretty hard. You need to start pulling some tricks, and 300 is pretty much not possible, or you need every trick in the book. And then above 300, it's just not going to happen. So thick parts are really fundamentally hard to image. So that's the half value layer. Just to give you an example of spectra, if you're not familiar with it, this is our Microtron with actually measured spectra. So you have photons per MeV on the left, so how many photons at that energy, and then you have the energy on the right. What you see here is that, we say it's a 20 MeV source, and note that this is a log scale on the left. You're actually getting very, very few 20 MeV. You're down well below 2 orders of magnitude from, say, this is probably about 500 keV. So we normally put a beam filter on this and we turn it into kind of, a big bump here. But these sources are not ideal. There's not a monochromatic source of the 8 MeV or 4 MeV. What we're dealing with is a spectrum. And so this adds to making the imaging of really thick parts harder. The reality, though, is when someone takes a 6 MeV and they image like a steel casting, it's this stuff down here in like 1 or 2 MeV that's doing the work, because their detector's better at picking that up. The nice thing is you get a lot of this energy when you have a higher endpoint on your source. So this also highlights, I said that for copper it was about 8 MeV right here, and for lead it was, I don't remember, 3 or 4 MeV. It was somewhere down around right there. So the only thing you're getting by going up above 10 or 10 to 15 is more X-rays. You're not necessarily getting better penetration. So this is why you see a lot of like 6-9 sources around the world. It doesn't necessarily make sense to go higher. It just gains you speed essentially. So got that. Just a quick thing on X-ray versus neutron. I mean, I could give an entire talk on this, unfortunately, but X-rays fundamentally interact with electrons in the majority of their interactions when they go through a part. And if you think about the cross section of, or the number of electrons, as you go up in atomic number, the number of electrons you can interact with goes up, just, with that atomic number. Neutrons, and this changes at very high energy. It's actually the interactions with the nucleus that start to drive X-ray cross sections when you go really high. Neutrons don't care about electrons at all. They're neutral charged. The electrons are tiny. They got no mass. So neutrons interact with the nucleus. And what that means is that your cross section is driven by the size of the nucleus relative to the density of the material. So it's actually the physical cross section of that nucleus as you go through. This leads to completely non-intuitive cross sections. So this is thermal neutrons. It changes with high energy, and they jump all over based on energy. The cross sections are really weird, but thermal is a nice example of hydrogen and boron down here have a cross section that's like 2 orders of magnitude higher than lead. And this is where the classic example of neutrons imaging rose through a lead cask comes from. But the trick is just that, yeah, you can use neutrons to get around some of your really dense imaging problems in some cases because of this strange cross-section behavior. And honestly, it takes an expert in neutron cross-sections to really tell you what the right energy is. So they're not common because of the sources, but they do have some strong niche applications for imaging. Okay, so I'm getting closer to real data here. Few key thoughts for high energy X-ray and neutron. So the other big deal here is safety, actually. And honestly, I think this is probably, it's safety and facility costs is why these sources are not common. So above somewhere, it's actually above 4 MeV is where you can start to activate materials. There's a few bad actors. And so what I mean by activate is your X-ray actually knocks a neutron out of a material, and either that material becomes a radioactive isotope or another material absorbs that neutron and becomes itself a radioactive isotope. So you can actually, like our source puts out enough neutrons, you can make a crude neutron image with it at 20 MeV. So people fundamentally don't like radioactive materials just wandering around. So with high energy X-ray, you can actually activate parts, and you have to survey parts and you have to wait for that activation to die down. And this can be pretty bad. I had some Inconel recently that was activated for almost a year. Gold's another bad actor. It'll activate for about 3 months. And so people don't like that. The other thing is, a 450 source it's not something you want to walk in front of, but it's not going to kill you instantly. And, our microfocus cabinet sources are the sort of thing that, a dentist uses. So they carefully measure the dose, but it's not fatal. Something like our Microtron will kill you in a minute. That's just, you're going from like a source that's not something you want to play with, but it's not too bad, to a source that'll kill you. And so all of this wraps up to, it's not that easy to install one of these sources. There's a lot of regulatory burden. Then the other thing is, shielding wise, you need on the order of, somewhere between it's actually somewhat above 3 meters of heavy concrete. So this picture is our Microtron I already showed. This is just the coffin around the source. So it's the shielding just to minimize scatter. This is an 12-inch thick lead wall and then 7-inch thick tungsten collimator. That's what's used to cut our beam down. The beam stop at the back wall on this building is about, it's between, let's see, what is that? Sorry, I got to think in meters, 3 and 4 meters thick. And we have a 100-foot downrange exclusion zone that no one's allowed to enter when the source is on. So these things just pour out radiation. This is the building where, and unfortunately, so this building was built in 1948 that the Microtron's in. This building was also 1948, or this bay we're putting our LINAC in. We've added a double layer, so it's up to about 4 or 5 meters of reinforced concrete for the LINAC right there. And because we get scatter out the windows, we've also still got an exclusion zone that goes further than where this photo is taken from. So this is the real deal. And a source can cost $1 to $3 million is pretty typical. Something like the Microtron's more expensive. The building can easily cost 10 or 15 million. So the price here is what really drives why people, price and safety, why people don't have these. So I think that's about it for the background. All right, one other thing. So the other trick here that's sort of worth having in your head is that okay, so suppose we found our X-ray energy. Now we're going to penetrate our part that's like, I don't know, 20 centimeters of steel. The question is now, how am I going to actually stop that X-ray and count it to give me an image? Because now my, I have an X-ray that will go, or neutrons, the same deal. It'll go through almost anything. Now I got to stop it and count it. And not only that, I want to do it with high resolution. So today what you get is you get a metal sheet and then a standard flat panel detector with a scintillator. And the high energy X-ray hits that metal, hopefully interacts with it, but our efficiency is well below 1% because we got this high energy X-ray that'll penetrate almost anything. That showers particles and the scintillator picks those up. So this is what we use today. It's been used in film forever, like lead and tantalum intensifiers for high energy film imaging. So this is, you go to like PerkinElmer, you say, I want to buy your high energy detector. They'll sell you something. I think it's a copper intensifier and a scintillator. And you've got less than 1% efficiency. And the bad news is you're also well above 1% efficient at picking up the lower energy scatter. So you're really good at picking up the scatter you don't want. You're not so good at your signal. So where we're working right now, and people have built these for like scanning arrays for security, or there's a few camera systems in the world. You can go to millimeter or even centimeter thick monolithic scintillators and then use a camera to pick up that light or possibly couple it to a flat panel. The problem is you lose resolution because your high energy X-ray comes in, it hits, you get, I'm trying to show here, you can get light, which goes a long distance and you pick up. So a lens on a camera will reduce that effect. Or you get multiple scatter of different high energy particles from this impact. And that causes a kind of a penumbra of where your light comes from. So that hurts resolution. And then you can go to a pixelated detector. So you take the same idea, but instead you put little metal barriers in between each pixel. And then your light is constrained and your scatter is constrained. But now you got to build this pixelated thing. So scanning array detectors are like this, but they're fairly expensive. And when you start looking at building one of these for a flat panel, you're rapidly into the few $1 million for a scintillator cost. So this is what most of my research has been recently, is trying to get this to a workable solution. And we're getting pretty close on it, but it's just a tough area. And so this is where you can get some extra penetration out, or some extra, ability to image thicker parts. But it's challenging, and there's not very many places that work on it. So I put this in because this is actually, I think, kind of important. So, I just kind of said it's really hard. It doesn't work super well in some cases. We got an expensive source. It's dangerous. So why bother? There's many standard reasons for imaging. You guys all know those, so I won't go through them again. What's happened in the past is we did high energy imaging, but we built it around certified material and welded parts. So, we get some material, we get really good at making it. We're sure the material's good. And then we're not so sure about our weld. So we use ultrasound and high energy radiography to look for like pores in that weld. So we spend all this effort trying to inspect just one weld on, honestly, it's like ships and, nuclear reactors and these, or infrastructure, real high consequence things. We'll still use high energy X-ray. You see, a few presentations at conferences. There's a company, I believe, that actually CTs cars and reverse engineers them that way. There's someone in Europe was CTing wrecked cars, and then they use that to study, how they make them safer. Those aren't paying for a lot of systems, though. And people, like I mentioned, infrastructure inspection. What's changed in the last few years, though, is large metal 3D printing. So we're seeing parts now that, and I just grabbed this article to give you an idea. These guys are claiming they're going to 3D print an entire rocket. But we're definitely seeing articles about people 3D printing both components of rocket motors and components of jet airplane engines. And it's pretty intuitive. You don't want either one of those to fail. And if anyone's looked at 3D printed parts, these things are not perfect. There's little holes and voids and pores all over the place. So what they've realized is they can make these parts and they have absolutely no way to certify them. You can't do ultrasound on the entire thing. The only thing that'll penetrate it is high energy X-ray. And so 3D printing is driving the development of new MEV imaging systems. And obviously you can also get to a situation where you can print something, you're not totally sure you got what you want. And so what you want to do is CT scan it and then put an as-built model into your code and model its behavior from there. So there's at least 2 companies in the US building new 6 or 9 MeV imaging systems specifically for 3D printed metal parts. And we're talking, you know, millions of dollars for the building plus millions of dollars for the source. So from my perspective, that's actually what's driving new interest in high energy imaging. Okay, so we got that. So now I'm going to go through some example MEV scans just to kind of give you a feel for where we're at. This is actually probably my favorite thing I've ever scanned. It was a small business. So we're supposed to support small businesses in the local area as a government lab. So this artist actually asked us if there was a way we could make a surface model of a 18-inch tall bronze statue of Christ in 3D, because she was trying to scale it up to a 24-foot statue. And what they do is they build them in segments, and then they attach those segments together. And then I hadn't appreciated this, but the statue is also distorted. So you have to make it fatter at the top and skinnier at the bottom, so that a person standing where you think people will stand sees it as a normal shaped person. So we did this at 6 MeV because we really didn't want to activate the thing. And this was actually what I'd call really a pretty easy scan. It was 18 inches, so it was bigger than our detector. And you might get the feel from this picture. I should mention our setup's very homemade right now. We've got a new commercial manipulator coming in, but this is a turntable set on an optical table on a hand crank lift table. You know, we've got an old adjustable collimator. I don't quite, the panel's right here. That's the statue in front of the panel, but you can do CT with a really crude setup. And we still shoot film here, so we wheel this out of the way and back in all the time. And so this was 2 scans. The bottom scan didn't need very many views. It took like 45 minutes. So really what I'd consider a very easy scan. And the data actually turned out quite well. So this is the 3D surface of it. I'll have another slide on this. This is a slice through it. You can see it's hollow, but you know, you got like the arms are put in. This is the 3D model in a artist visualization software for where they're going to build the new statue. And then this was really unique for me. They actually took the statue right after we imaged it, flew it to Rome, and it was blessed by the Pope. So that, you know, imaging a part that was in blessed by the Pope was kind of I feel like a highlight of my imaging career. So that's the basic setup. And just to give you a feel for where it's at, so if you calculate along the arm, we're 14 to 15 centimeters thick along each arm. So, you know, we're starting to actually hit that limit I mentioned of this is getting pretty darn thick for imaging. And what you can see is there are scattering and a little bit of beam hardening artifacts. So I don't know how this comes through on people's monitors. Maybe it's actually better than a projector, but there's kind of a penumbra here. You see the wrist is a little darker. So what this turns out is that if I do a surface fit right here, I'm trying, you know, like I see all these little features, but I just can't get the surface to follow it as well as I want, or I start to lose the wrist. And this is very typical of high energy imaging. And so this is what I'm trying to get rid of in improving it, so that we can actually do, you know, so that I could come in and I could get these pores in a model, I could get these edges. Obviously, someone who is really good at coding could probably build an algorithm that would find these things. But this gets worse when you get to thicker parts and higher energy. And in our case, our homemade setup wasn't quite perfect. So there's a little geometric error there on the fingers. Probably the beam center was a little higher, a little low. But this really worked quite well. And it was, you know, like an hour and a half worth of work. So not bad. And I have a nicer detector now, so we would do somewhat better today. But we were constrained to 6 MeV because there's no way we could risk activating this thing and then not being able to give it back to the artist for, you know, 6 months or a year. Just to show the detail really is quite good. So this statue has etchings all over the surface of it. And just looking at, you know, so this is just a 3D rendering where I zoom way in on the feet and the legs. And then this is a partial surface fit to one little area. It's like the largest part of that E is 0.76 millimeters. Some of the smaller stuff here, I mean, we're well below 0.5 millimeter. We're probably actually hitting like 200 microns. So the capability is pretty good. We can get a few hundred microns of imaging resolution without too much trouble. The problem is artifacts here make really fitting that tough. So that's the statue example. This is another neat one we did for the New Mexico Museum of Natural History. So this is everyone calls it the T-Rex. It's actually, it's called the Bistivaris something by paleontologists, but we shortened it to the Bisty Beast. It's a predecessor to the T-Rex that was dug up about, I think it's about 200 miles from where Los Alamos is. This is it on display at the museum. They wanted to CT it to get the structure inside the brain cavity to understand where it fit in the evolutionary chain. And it turns out that's quite hard to do. So it was kind of a neat opportunity for us. We tested 10 MeV on a small piece of it that they were willing to risk, and it didn't activate. So we were able to run at 10. We also did fast neutron imaging on it. Unfortunately, the field of view on that was so small, they're still trying to piece the data back together. And then they built a custom drum for it. So this is a cardboard drum with a carbon fiber clamshell inside of it that sandwiches the thing so we can handle it. And this is the two paleontologists on the right, and then the teams that did the neutron and X-ray imaging. Here's a better view of the Microtron bay. So the machine's behind us, and we don't have our imaging set up. So that's that. So I mentioned the custom drum. We did also put, so we knew we'd have to scan this in multiple parts. So we put steel bearings in the that carbon fiber clamshell. You can see them right here to aid in stitching it together. And just to give a feeling for the field of view, this is what the width of the panel would do. So that's about 41 centimeters. So we actually had to do a half scan on it as well. But you can see you get some nice detail in there. So with all the scans, it was 4 half field of view scans with 4,000 views. We did one of them with a 100 micron detector and the rest with a 200 micron. So we ended up with a terabyte of data. And so we only had a couple machines with enough memory to even load this entire thing in 3D. But yeah, so that's kind of the setup. And then showing some results. We didn't spend a huge amount of time of stitching on this, honestly, because we just, they weren't really paying for it. We did it more as a show what we can do. So the paleontologist really did the interpretation, but the data looked pretty good. A lot of this is just cracking in the bone or in the rock that it became. You can see stuff like, so I hadn't appreciated T-Rex are like sharks. They grow new teeth under their old ones. So this is a tooth right here that is growing out. So when this tooth falls out, the new tooth will come in. You can see, there's a few scatter artifacts around the edges. There's some stuff right in here, but it actually, they were quite happy with the quality on it. And this was a very homemade setup in terms of getting the turntable in front of the detector. We really had to sort of move tables around and change heights. And so it's not the prettiest system. They got a really nice paper from it. So it was published in the anatomical record. This is the author's paper description and so on. And so they were able to get what they wanted in terms of the sinus evolution. And this places it in the evolutionary chain. You think about it, I mean, when these things are filled with rock, unless they want to destroy it, they have no way to actually do this work. So there's a lot of these things sitting around. If it's fossilized where they can get into the brain cavity, then they can measure it. But if it's in a chunk of rock, they can't do anything with it. And so this actually was a very useful capability for them. I've got no idea what any of this actually means, but they were able to segment and find all the things they want and label it. And so they were pretty happy with it. So that's another example. And I'll show, this is, this was made off a surface fit, so it does show what you can do, but I just feel like when you got 3D data, you got to show one movie at least. So this is just rotating around. The skull looks really good in one view, and then it's kind of squished from the fossilization process. So it's not quite as spectacular in person as you might hope, but it's still really cool to take a X-ray image and see a bunch of giant teeth in it. That's here, and I think I'm getting a little close on time, so I'm going to try to speed it up a little bit. This is just it's called a mid-scale test object. It's purely that because it's not small and it's not large. This is what I actually normally work with, is someone's got some like piping system or shielding system or whatever, they want to inspect it. So this thing's got stainless steel fittings. It's a big stainless steel can. You got a tungsten slug in the middle for high density. They put some wires in here to represent features they want to look for. And then they got nylon around the outside. So you're checking how well can you see the low density as well as the high density. And the smallest features, I think, in this one were the 0.5 millimeter molybdenum wires in right here. And then there's actually a hole with no wire that's 0.5 millimeter up there. And this was, I'm just noting, this was done on an older PerkinElmer 200 micron panel. So we do have a nicer 100 micron if we want to take the time now. So we could do somewhat better. But I wanted to just highlight a few of the sort of issues you see. So qualitatively, this actually looks pretty good. But then you go, well, I want to do a fit. I want to be quantitative. So this can edge right here is stainless steel. These are also stainless steel. They're the same material, as is this. So what you see is the combination of scatter and beam hardening makes the attenuation values very different between the thin and the thick regions. So I can actually go in and tell you if like there's a flaw here. I mean, you can actually see a gap right there if you zoom in. You can see all these little features here, but it's awfully hard to do automated computer analysis when you got this kind of variation. And then you also see like on the tungsten, you get this streak. So this is tungsten, this is the same piece of material, but you get this streak from the beam hardening and the scatter. So if you get better detector, this starts to go away. If you can stop more of your beam, you get more signal. But that's the sort of thing you always deal with high energy. Same time, you can see like really nice thread detail on this thing. So the resolution's quite good. You know, you do get, so this is that 0.5 millimeter hole inside nylon. So this is showing, you can see a really small feature, even though we're using I think this was a 6 MeV scan. And this was actually on a not totally, this is our portable 6 MeV source. So it's not the best source for imaging, but our Microtron was dead at the time. So, you know, you get, this is 8 centimeters of steel. So you get pretty good detail through it on all these seals and stuff. The penetration works well. There's they had a piece of poly in here as well as a nylon. So you can actually tell the difference between the poly, the nylon, and this is a Viton O-ring, like a seal you would have on a pipe or something. So by eye, it's quite good. For automated, it's not quite as nice as we'd like. I did want to throw this in. This was actually the highest density thing we ever successfully imaged with fast neutron. So this is a uranium cylinder that is, did I put the numbers in here? Oh, darn it. It's, now I'm gonna have to go off memory. It's about I want to say a 10-inch diameter uranium cylinder. And so this cross section here, I want to say you're getting into the like 15 centimeters of uranium to penetrate it to image. And then what we did is we put in, this is a little chili pepper that's made out of aluminum, and then pyrite crystal. So that's, what is it, iron sulfide. So these are both much, much lower density, lower atomic number than the uranium shielding it. And this is actually a rubber cork, like a decorative cork for putting in a wine bottle after you've opened it. And so this was a 13-hour scan at LANSCE at that gigantic facility, and you can tell the noise level is just not awesome. And the problem is we got neutrons that'll go through, you know, 10 centimeters of uranium. Now we can't stop them and count them. And the source is not bright compared to an X-ray source, but I can see rubber that is shielded by, you know, somewhere in the vicinity of 10 centimeters of uranium. So this was painful to get, but if you had to look through something dense and say, check like a, I don't know, a rubber seal or something like that, fast neutron can do it. It's just, there's so few sources, and it's, you know, there's just not much development on the detector end. So it's not as good a quality as we'd like. Second high energy neutron example, this is it's a tungsten cathode for an X-ray source. So this is about 12 inches across right here. It's, the bottom is solid tungsten, and then the middle is just hogged out empty. And then this is a channel that's been cut out of the tungsten, and it's got, I didn't write it on here, I think it's also a molybdenum wire, some kind of denser metal wire running around the inside that heats the whole thing. And then that's potted into a ceramic, and this runs at high voltage. And so if you get a crack or a void, that'll cause it to arc and your cathode's no good. And the machine this goes on, I think they said it took them 2 days to change it. So they don't want to just change it and then have it go pop like a light bulb and have to put a new one in. This was one that had already failed catastrophically, and they wanted to see what we could image. So this is looking at your cross sections through the scan. And what it turns out is you can see the cracks in this ceramic, no problem with the high energy neutron. We tried this with X-ray pretty hard, and we could not see this ceramic at all. I've gotten better since then, so maybe I could make it work. But this was a case where the high energy neutron just worked really well. You could see the ceramic shielded by tungsten without, you know, it's noisy, right? Our resolution's not what we want. Our noise is not great. But if we, you know, took 5 days to do the scan, this would get better. So it's an example of where, yeah, it does work. It's just kind of a niche application. And this is not really high energy, but I threw it in just for a note because thermal neutrons are kind of weird. There's specific energies at which a thermal neutron will go through one material type with almost no attenuation. So lead's the classic example. There's some energies in neutrons that'll penetrate lead basically without stopping. The same thing's true of, I know it's true of uranium for reactor work. I think for some, you know, something like iron, you can find the same thing. So you can use a thermal neutron to penetrate a very, very thick sample if your sample is like one material. The problem is if you got a sample and it's got plastic around it, plastic stops thermal neutrons like crazy. So it's niche. It has to be a very particular part, but it can be useful. And I threw this in just to highlight the, so you could take something like plastic inside a foot of lead and you could image that plastic, no problem. And this is showing, this is actually a Mac Mini computer we did on a 450. X-rays are interacting with the metal. You got an aluminum case, this is a copper wire that's got plastic sheathing around it for, I don't know, I think it's for the fan. This is your motor on the fan. If you look at the Neutron, what you get is these little plastic supports inside show up like crazy. And then the sheathing on the wire shows up as well or better than the copper. And then it's sort of not intuitive, but this image on the right is actually property stickers that we can see on the outside of the case with the Neutron, no problem, because they're plastic. So they show up really well. So that's just something to keep in the back of your head. There are some niche thermal neutron applications that'll penetrate very, very well. And okay, I think I'm almost done. I got to where we want to be a little bit on Scintillator. So this is just a note. I think you guys are well aware of this, but where we want to be is like what we can do with a microfocus. So this was a steel tube that we could penetrate at 150 kilovolt. And we can read it in. This is a wall thickness analysis. So every variation you see there is where the tube was bent and it stretches a little bit and the wall thickness changes. And this is just a simple analysis to do. The data is so good, you can load this into something like volume graphics, you can do your analysis and you're done. This is the same idea, but it's actually a hard-boiled egg that someone dropped on the way to the scanner. Turned out it made a great data set for showing thickness variation because it turns out eggshells are not uniform thickness. And even though it's in pieces, the code did quite well at getting the thicknesses through those shells. And then this is, I think kind of like any number of presentations. This is from synchrotron data looking at porosity in a urania sample. And someone, a modeler wants to do something with this porosity, basically. So this is where we're trying to get with high energy X-rays, data quality good enough that we can do this type of analysis automatically. So this is just showing a little bit. We're switching to buying new manipulators, getting just a nicer CT setup. Scatter control is a big deal, so a little bit of improvement on collimation, large bays. The main thing though is detector improvements. So this is two examples. This is a 1 centimeter thick tungsten bar, and then each little thing in here is a glass scintillating fiber inserted in that bar. So as far as we know, this bar has more hand-loaded scintillators than any one in the world that's ever been made. And what happens is that tungsten acts as a converter, and then the glass scintillators scintillate when energetic particles coming off the tungsten hit it, and that gives you something like it's a centimeter of tungsten. It's like a 15% efficient detector. So this works pretty well, but the problem is this thing was, I don't know, $300,000 and took a year to make, and I want one that covers an entire detector. So we're working, the problem is you've got a manufacturing issue. This is a similar idea, but it's a large circular array made out of 4 centimeter thick BGO crystals. So BGO's got a density of like 7 grams per centimeter. So this is a massively thick detector. This works really well, but about the smallest you can make the pixels is 1 millimeter, so you're resolution limited. And I think this was a couple $1 million 20 years ago. So, it's a manufacturing problem that if society wanted to make hundreds of these, they wouldn't be that expensive. But when you want to make one, they're horribly expensive. And then the other idea that's out there is if you can make yourself a microfocus source, you can reduce scatter just by moving your part away from your detector. And then you can use something like these 1 millimeter pixels and get your resolution back. So we've got some work going on making like 100 micron spot size source, which will actually get rid of a lot of these problems. And then the other thing that's worth mentioning, you pull tricks like this is commercially available in 450s now, but not done so much at high energy. You can dither your detector and get resolution back. So we've done work showing that if we can make say a 0.5 millimeter size pixel and then dither the detector, we can get back down into the couple 100 micron resolution range. And this is just showing, so no dithering, what you get with dithering. And then this is our gold standard still is actually film with a converter is a very high resolution. And I actually can't see it on my screen because of Zoom shows little windows there, but the furthest out hole like here versus here, we're actually getting better with a dithered digital detector now than with the film standard. Oh, and this, so this is our new 915 LINAC. Unfortunately, we're stuck in an old building, so we got all this jury-rigged shielding, but that's the lead wall to check how much, this isn't final, but that was to prove the thickness of collimation we needed to keep the scatter out of the source down. So I think that's at least 12 inches. It's either 12 or 16 inches thick lead, and that worked pretty well. So that's sort of what you're dealing with. And then we're putting a new commercial manipulator in with all the motion, and then a detector that dithers around. Then you have to dither the collimator with it to keep from frying the electronics on your detector. So this should help our repeatability quite a bit. So, you know, this is just summing up. MEV X-ray CT is really a growing field now. Metal 3D printing is driving it. I'm hoping that this will actually force commercial companies to start working on improvements, because there's only a couple people in the world that have been trying to really improve this, and doing stuff alone turns out to be really expensive. And I'd rather 10 people worked on it. We could all buy the same thing. You know, I went over expensive and safety hurdles. MEV Neutron CT can be done. I'm very, very lucky in that I have access to a source that I can use, but there's just, you know, there's very few sources, and honestly, there's very few people that even know how to do it. So it can work in niche applications, but it's a pretty rare field. And then from my perspective, our current detector is less than 1% efficient. So that means I got a long ways to improve right here. And detectors are not that expensive compared to the source. So this is currently our major thrust for, you know, if I get to 5% improvement, I've already made a huge difference over where I was, or sorry, 5% efficiency. So this is where I think in the next couple of years, we should be seeing some significant improvements that get the data quality better and faster scans. I think with that, I got just acknowledgments for all the people that contributed to this work. And then I got to acknowledge the Neutron Center, and one of those images was from the Advanced Photon Source up at Argonne National Lab. And so I think that I can just take questions.
Great, thank you so much for that. As with the other talks, please put them in text chat. So we've already got a few coming in. So from Sharif, we have you considered super resolution imaging to improve resolution?
So I think the dithering is actually technically a type of super resolution imaging. I've not considered, I know, for example, the Neutron guys will do multi-source. I guess part of it is what do we define as super resolution? There's a multi-source technique we've not tried. So I'd say we've dabbled in that a little bit, but not a lot. The other issue we run into is actually time. So a good scan on a large part is like 4 to 6 hours. And the reality is the way most of our facilities run are kind of shifts. And so you know, the Neutron facility, we've done like 40-hour scans, but in general, I can't unfortunately trade. I can maybe double the scan time, but I can't go a lot longer than that. And even something like dithering, I got to take 4 times as many views minimum to get it to work. So I don't know if that answers, it would depend on the super resolution technique, but we've really only dabbled in it a little bit.
So the next question comes from Charlie Woods. Great talk on high energy imaging. Out of curiosity, what do you do with any of the activated samples after data acquisition?
So there's 3 answers to that. The reality is I'm at a federal lab, and so a large part of what I image is already radioactive. So our normal procedure is that there's limits on how much you can ship. So our problem is when it leaves our facility, if it goes on a public road, if it's within the standard shipping limit, we don't do anything. It'll die back down on its own. That's for radioactive samples. The normal thing is we actually have to hold them at the facility until they've died back down. So I've had this Inconel sample, we had surveyed it at 6 months and it was still a little bit hot. And then we surveyed it, the virus kind of shut us down and we got distracted and forgot to check it again. And so at a year it wasn't hot. And so that is now with free release, we can return that part. And then in a few cases, so for example, we replaced the lead wall on that facility with painted lead because of just lead contamination issues. Turns out that there's trace elements in the lead that activate, and that lead had been sitting around that source for like 15 years. So that has to actually be disposed of as radioactive waste. And so that would go through that waste chain, which is quite expensive. And so this is why people don't like these facilities, right? So the optical tables activate, and if you figure that table's been there for 40 years, most of that building will go as radioactive waste when it's torn down.
So what's the difference between, you mentioned earlier, even with the X-ray, you'd get some activation at such high energies. Like how long is I mean, I guess it depends on the material, does it?
So it depends on the material, and it depends on the energy of the neutron. And so typical activation requires neutron absorption. So it turns out, and this, I didn't appreciate this till I did fast neutron imaging. If you use cold or thermal neutrons for imaging at a reactor, that really activates materials. And reactors are really good at this. They have specialists that'll calculate. I mean, you can get a material hot enough you can't even approach it. So that's because they're low energy, so they just hit the material and they basically grab onto a nucleus, and you then have a radioactive isotope. The fast neutrons actually tend to just get deflected when they hit the part, and they'll absorb somewhere. It's probably actually going to end up like in the concrete walls or something like that. But the high energy tends to activate a lot less, and our microtron, it usually puts out a few MeV neutrons. So we get some activation, but it's not terrible. And then it depends on the half-life of the material. So we actually discovered doing some work on virus sterilization that we could activate a Ziploc bag like it pegged our meter. It was actually so hot, it was above it at 20 MeV, but an hour later it was nothing. It had died all the way back down. Whereas gold is used to measure your number of neutrons. And so it's got a very well-known half-life that I think 10 half-lives is the rule of thumb for you can no longer measure it, and for gold 10 half-lives is like 3 months. So the problem is you need to know what you're doing. Like a company can't just buy one of these things and start using it. They have to actually typically prove to the state or the government that they know what they're doing and they have the ability to control the hazard.
So another question that's come in from Giles Aldrich Smith. Can you talk about the use of graded collimation to improve image quality?
Yeah, so Giles he's pulling a trick here because I've collaborated with him in the past, so he knows. So this is what in low energy imaging would be called masking. And so if you want to penetrate a sample that's a little bit too thick, so you're saturating your detector on the sides, one option you can do is you can actually cut a mask out that would cover all those areas where you're saturating it, and you're only putting X-rays through your part. This moves scatter away from your detector. It keeps your detector from saturating. The problem is traditionally you cannot reconstruct a computed tomography data set with that. So someone would mask like on a steel pipe to see a weld really well, and they just blast it with the source, and they get more signal through a thick region. We figured out a method that it's called graded collimation. It's been used in imaging for years. So rather than a uniform mask, like you just shield it, you can make kind of the inverse shape of your part, and you can get, sorry, I try to use my hands talking and no one can see my hands. You can flatten out the contrast required from the thickest region of your part to the open area of the detector. And you can do that across a gradient, hence the term graded collimation, or it's in optics, it's called an apodizing filter. That's been done in radiography as well. What we figured out was you could actually calibrate that if you used your graded collimator in your light image, you could actually calibrate that back out of the CT scan and end up with a image that could be reconstructed. So that's one of the tricks we pull for very, very thick objects where, it's a little bit about fixing the dynamic range on the detector, but primarily we put this graded collimator in front of the part near the source, and that moves a large source of scatter back away from the detector, and we get a better signal to scatter ratio. So the problem is you got to have a part that's symmetric so that you can rotate it and your mask fits as you rotate, or you have to have an adjustable collimator. And that is used in cancer therapy imaging. I've never heard of anyone doing it for actual something like for high energy tomography.
Thank you. Do we have any more questions, or does somebody want to field one from the floor with their microphone?
Ooh, I have one. If you can hear me.
Yep,
I can hear you.
Cool. So with MEV, you know, when you go beyond 1 MeV, you suddenly the physics goes a bit wonky with regards to imaging. Please, can you just enlighten us about the artifacts that we tend to see? What kind of artifacts do you tend to see and deal with MEV imaging? I know you've touched on the half value layer, but would you mind just telling us a little bit more about the kind of other artifacts that you tend to have to deal with?
So the main artifact that I guess there's two primary ones. The one that everyone's familiar with is called beam hardening, right? So we have this broad spectrum as it goes through thicker regions of the part. The spectrum tends to harden and you get less attenuation in those thick regions, and it causes like a black area. That still exists at high energy. The other one that what I refer to it as scatter, and this is kind of where your physics question comes in. There's, in a really simplistic model, there's particles that went through the part without interacting, they hit the detector, and that's my signal. That's what I want to measure. Then there's particles that hit the part, and what I hope is they just hit the part and disappear, but they don't actually do that. And so in low energy, you pretty much get scatter is a fair term, right? You get either the X-ray is deflected, or in a few cases, it knocks an electron out, another electron drops in, you get re-emission from the, one of the, like the K shell or something. And your part is basically a little source. And that can happen in your detector as well, like metal around your detector and the back wall. We get the same effect in high energy, except it's a lot more complicated. So, we talked about the fact that the source generates neutrons. That's this giant resonance neutron production from high energy X-rays. And I honestly don't really understand the physics. I just visualize it as X-ray hits, neutron comes out. I don't want that neutron. And the same thing would be true if my X-ray hits and deflects, which can occur, or it can even not do stuff like knock off a high energy electron that I pick up. Unfortunately, we use gadolinium oxysulfide, or GADOX, in a lot of detector scintillators. Turns out gadolinium's got the largest cross-section for thermal neutrons of any material. So we're good at picking up stuff like a thermal neutron that's been bouncing around the room after it came off the source or the part. So I guess the short answer is there's a lot of effects going on, but at the end of the day, what it comes down to is I pick up particles that I didn't want, and there's a lot more of those in high energy, and those are what we lump into the term scatter, and they have an effect that's very similar to beam hardening. You get like an inside edge will get fuzzy, so you can't see it very well, or it'll totally disappear. So I don't know if that helps, but it's actually really comes down to it's almost all scatter artifacts. You do get some stuff. I don't know if anyone noticed the T-Rex image, there were a bunch of stripes through it. That's actually the fact that our these high energy X-ray sources are basically a giant electromagnetic pulse system. And so they interfere with the electronics on the detector. And so it's pretty common to get stuff like that, and there's ways to remove them. If you're using a camera system, you also get X-rays just directly impacting your camera and causing bright spots. So those aren't too hard to remove, but at the end of the day, it's actually the scatter that kills us. It's just that we pick up a lot of diffuse particles that were not signal, and then we get this scatter to signal ratio that's really bad.
Thank you.
One of the reasons people use fan beams, but obviously things take a lot longer because.
Right. Yeah. So we definitely do that. I have one scanning setup. It's sort of a pseudo fan. It's about a 1-inch fan beam, but you can collimate that way, and then you can also build a linear. So like the ideal detector is a single pixel where you just scan it around. You collimate everything out, so you're picking up almost all signal and very little scatter. And your scatter is proportional to the area of the beam that hits the part, loosely speaking. So if you go to a fan beam, and if you say did 10 pixels tall, and you had a 2,000 pixel detector, and you collimate your beam to fit that, you've just reduced your scatter by a factor of, what is that, 1 in 200. So you're down to 0.5% the scatter you'd have had with a direct view. So there is always the option to go back to a scanning array system with a collimated source, and you can eliminate most of these artifacts. The problem is the time involved is just huge. And so at least for the sort of operations we do, we just can't afford the time. Like we could inspect a weld on one plane that way, but if someone gives us a part that's a, you know, like 3D printed metal that's all weld, it's going to take forever to inspect.
So touching on that, you were talking about the scintillator efficiency at like 1%, which really surprised me. So does that mean when you say going up in efficiency, does that mean that you're improving the resolution, or that you're reducing the time it would take to scan?
So what you're doing is you're improving the detection efficiency. So if I take a scintillator that's twice as thick, it's got twice the probability that it'll stop an X-ray and be able to count it. So in general, people do this by going up in thickness. So instead of, I mean, our setup's like a, you know, a half millimeter of metal. And you got to appreciate that it's actually the metal that does the stopping of the X-ray. And then the scintillator is a conversion from scattered particles off that metal to light, which the detector picks up. But what it's actually doing is it's just giving me more signal. And in general, the signal ratio climbs faster than the amount of scatter you detect, because the scatter is lower energy, so you're already getting most of it. So you're increasing your signal to scatter ratio, which can be a faster scan. So if I get twice as thick as a scintillator, hopefully I get about twice as much light. Now I can scan twice as fast. But what's actually important is that hopefully I now have twice the signal to scatter ratio, and that means these artifacts are not as bad. So we're using it more to reduce artifacts than to increase speed. So I don't know if that covered it perfectly, but it's a little bit of a mind bit. You got to really get in the framework. It took me a couple of years to get to where I was like, okay, I know what I need to build. Now it's how do I build it?
Yeah. Great, thank you. Are there any more questions?
Can I ask one question?
Sure.
I mean, you said that the scattering is the most important contribution for the artifacts, right? Then,
correct.
I mean, for low energy neutrons, there are techniques to measure the scattering. It's so-called black body bias correction was implemented at PSI. Then they basically use a tiny gadolinium mask in front of your sample, and then you measure the amount of scattering after the gadolinium spots that you have in your image.
Right.
Do you think it's possible to implement also for high energy X-ray?
So there's a company that's actually building that. It's I can't remember. They spun off of GE up in Ohio in the U.S. That they have that technique in their commercial scanners for like 450, and they're planning on putting it on their 9 MeV. So I'm honestly hoping to see their results as soon as that's running. We have not. It's harder, right? You're talking like now you've got to build precision holes in a 1 or 2 centimeter thick tungsten plate. But the technique has been shown to work very well for cleaning up reconstructions, at least at lower energy X-ray, and as you mentioned, Neutron. The only problem, and this is where I think they're going to run into issues, is that what you're assuming when you use this technique is that you have some signal. So like you've got some good signal in your detector, but you're getting artifacts because, you know, maybe as much as like 70 or 80% of what you're counting is actually scatter. But you've got, you know, 10 or 20 or 30% signal. So if you can separate the signal and the scatter, you're in good shape. My problem is that I may well be getting, you know, 99.9% scatter and 0.001% signal. And so in addition to, so I think if I've got signal, yes, that technique should work if you can build the plate and get it aligned and do the measurement accurately enough. The problem is if you have almost no signal, then you're just stuck. It doesn't matter if you can correct it. If you're not getting anything through, there's nothing left to use. And I think depending, so like what I'd consider a medium part thickness or an easy part thickness, that technique should give you a really nice result. For the limit on like really, really thick parts, you're gonna have to, that technique might help, but you're gonna have to get a more efficient detector.
Okay, thanks.
Anyone else? So I think that's probably it. Nothing else has come through on text, so that just leaves me to thank you once again for well, I'm definitely hoping that I'll be able to use one of these in the near future. I know Tino and I have been discussing what we can do to get some samples out to you.
Right. Right. No, that's I'm looking forward to more people starting to use these things, honestly, because it would be great to have more minds really thinking and working on how to improve them.
Brilliant. Okay, well, thank you once again.